Hello, welcome to the SIG-Autoscaling deep dive. My name is Joseph Burnett and I'm here with Maciek Pytel. We're going to be going into some autoscaling topics a little bit deeper than the introduction. So we'll be sort of assuming that you know a little bit about Kubernetes autoscaling and that maybe you have seen the SIG intro. So here is our agenda. I'm going to talk a little bit about workload autoscaling, that is, increasing and decreasing the number of pods in a cluster. And Maciek is going to follow up with a little bit about a cluster autoscaling, which is increasing and decreasing the number of nodes on which those pods run. In particular, I'd like to highlight some new features in HPA coming in Kubernetes 1.18, which are called scale controls. And I think that it would be also helpful to go over a little bit about custom metrics in the HPA and the HPA lifecycle, so you can kind of understand how scale controls work. Okay, so let's talk a little bit about the recommendation lifecycle. So HPA, like every other object in Kubernetes, is something stored in etcd, and when you want to scale a deployment or another scale sub-resource horizontally, you declare your intent in an HPA object in spec, and the HPA controller tries to reconcile to that intent. So the first step in that reconciliation is to get the HPA object. The next thing is to get the target of the HPA, which is in this case a deployment or anything that implements the scale sub-resource. So the controller will get the current scale, then it will look at the metrics that you've defined for this HPA, and it will load them from the metrics server and put those two together and calculate what the new scale should be. So it'll come up with some recommendation. For example, if you've decided that you want your application to run on average at 50% CPU utilization, the HPA controller will get the current number of pods, maybe it's 10. It'll get the current CPU utilization from the metrics, maybe CPU utilization is 75%. And it will decide, okay, well, actually you need more pods to bring that down to the target. So it will give you 5 additional pods. Then after it's calculated the new desired state for each metric, it will limit and stabilize the maximum recommendation. So limiting is like not going above the specified maximum, not going below the specified minimum. Stabilization is a part of the algorithm that waits for 5 minutes before you scale down. So it actually keeps a window of recommendations for 5 minutes and chooses the maximum recommendation over that time. This prevents flapping, and scale down stabilization allows you to scale up quickly in response to new load, but sort of come down gracefully without flapping. So finally, when the HPA recommender has a scale, it will turn around and set that back onto the scale sub-resource, and then wait for 15 seconds before repeating the process. It does this for each HPA object every 15 seconds. It goes in this reconciliation loop, checking the current state of the world, making an adjustment, checking to see if it needs to make subsequent changes. So there's a feedback loop. So HPA has 2 versions available. There's V1 and V2. V2 is currently in beta 2. You can get them from the command line with these commands here. This is normal Kubernetes stuff. You just have to qualify V2. Don't look too closely at this. I just wanted to show you the shape, and I'm going to go through each one of these sections one at a time. So on the left-hand side, you can see scale target ref in V1, and it has the same thing in V2. It is pretty simple. It just points to some Kubernetes object. The second part of the spec is the metrics. So in V1 HPA, there's just one top-level target, which is CPU utilization percentage. But in HPA v2, you can provide more than one metric. So you'll notice that metrics on the right-hand side is a list. And this is what CPU utilization looks like for the new v2 metrics. So after the HPA has gotten your current scale, it's going to go through each one of these metrics, retrieving it from the server, and it writes the current levels to the status so that you can see in the status of the HPA object how the controller is doing towards reconciliation. This is nice for observability and just to make sure that it's doing what you expect it to. So I mentioned that HPA v2 can have multiple metrics. So the other kind of metrics that you can add in there to that list are called custom and external metrics. Custom metrics are anything that's inside of the Kubernetes ecosystem. So this is pods or deployments, ingress, whatever. There's two kinds of custom metrics. One custom metric is a pod metric, and so the HPA will expect to find one of these for each pod in the deployment, and then it will average them. For an object metric, HPA will expect to find just a single value. So for example, ingress could have QPS associated with it. External metrics are things that are outside of Kubernetes, could be some pub sub, queue, or something just simply entirely external. So these are fairly arbitrary. I want to take a moment and talk a little bit about how custom metrics are wired into the system, because this is something that's important to know if you're going to set up HPA on custom metrics. So the API server has a mechanism by which it can delegate calls to some objects to other API servers. So you can see there that the main API server has etcd storing things like HPAs, deployments, pods, etc. But when it gets a request for metrics, it routes it to a different server. There's a metrics server that's part of the normal Kubernetes distribution, which provides memory and CPU, and that runs typically in the user space of the cluster. The access pattern for a database like that is very different, so this is one of the reasons why it's a different implementation. It's a time series database, not just a key value store. There's another server that is in this routing path as well, which is the custom or external metrics adapter. So there is no default implementation for custom metrics in Kubernetes. This is something that you provide as either a cloud provider, or you can install Prometheus in your cluster. So for example, if you have a Prometheus instance that has the metrics that you want for custom and external metrics, you install an adapter that will take those GET requests to the API server objects and translate it into a backend query for the data source that you have. So this is where the data comes from when HPA retrieves it. So moving on sort of through the life cycle here, you can see that calculating the state is kind of the core value of the HPA. This is the part that's going to reconcile the number to try to achieve your target. So the current utilization is first achieved by either averaging all the pods or just taking the single value. And then it's going to be divided by the target. So say if you want 50% and you get 75, you end up with 1.5 times what you should have in terms of utilization. So you multiply that by the current scale, and that gives you the new number of pods that you should have. And then the next phase is stabilization, which I already mentioned before, keeps a 5-minute window. Now this is actually going to be configurable with scale controls, which is something I'm going to get into in just a minute. So there are a few, so the scale controls are a new field, top-level field in the V2 API. Inside of the behavior field is two structures. They're identical. One is called scale up, and one is called scale down. And each of these has a stabilization as well as relative and absolute policy that can be applied for limiting the rate. There's a couple of defaults that were already part of HPA, which have become defaults for the scale controls. One is that there's a flag on Controller Manager that sets the downscale stabilization window, which is by default 5 minutes. So this is the default for scale controls as well. And this is, as you can see here, inside the scale down structure. There was also a couple of defaults that were hard-coded into the controller itself. One was that it's okay for you to go from 1 pod to 4 pods, because this allows you to get off the ground a little bit faster for scale up. Because in order to scale up for something like CPU, you need to sort of scale up, see additional usage, scale up again, see additional usage. So this was sort of just a small optimization. And also there was a limit in the controller which said that you can only scale up by 2x each time, each reconciliation. So these become defaults in the scale controls, but you can change them. So for example, if you want to come down slowly, if you sort of expect your traffic to maybe come back, you can limit the rate at which you scale down. If you want to maybe have a shorter stabilization window to come off of a spike more quickly, or a longer one, you can set that. It's actually also possible to set a scale up stabilization window, which sounds kind of counterintuitive at first, but it could be useful for a batch workload where, for example, you have some number of pods running and a whole bunch of messages land in the queue. But you may care more about utilizing your pods and resources as efficiently as possible rather than latency. So you might want to wait a few seconds or a few minutes to wait and see if the pods that are already there can handle all the messages. So that's what a stabilization window could be used for scale up. So explore the documentation. There's kind of a cool feature that's there in 1.18. And there's a lot more details about what they mean in the actual Golang docs. So I recommend you go take a look at it. Again, that's in the V2 beta 2 HPA structure. So big thanks to Ivan and Arjun for writing the cap and doing the implementation and pushing this through for quite some time. It could be difficult to make changes in Kubernetes. It can take time and patience, and they definitely did a great thing here to put the scale controls in. So thank you. One last thing about the V2 API I'd like to mention before I close the workload section is that there's also conditions which are added to the V2 API in status. So conditions are a newer pattern, newer than V1 HPA, which just gives you some insight into how the reconciling controller is doing towards achieving your desired state. And if it's not in the desired state, why not? So it's kind of a structured way to sort of get some insight and observability. And there's 3 sort of types that are worth noting: scaling active, able to scale, and scaling limited. So I'd like to talk for a moment about what each of those means. Scaling actives means that you have provided metrics that exist, they can be retrieved, so it's possible to sort of know where we're at in terms of the metrics that you provided. So if scaling active is true, that's a good thing. Able to scale means that the scale target ref is able to be retrieved and updated. So that also should be true. And if it's not, then there'll be a message there to tell you a little bit more specifically what went wrong. Scaling limited is a little bit more of a just informative. It's not necessarily a problem if you're scale limited, because usually you're limited because of some policy limit or a stabilization that has been put in effect for a reason. So this is just for you to know that the raw desired number of replicas is being constrained in some way, either upwards or downwards, and this should also tell you why. So you can get some insight into how it's operating. So all these extra fields in V2 are backwards compatible. So you can actually retrieve any of these HPA objects as a V1 or a V2, and it's done losslessly by serializing all the new and unknown fields into annotations. So it's possible to interact with a V2 HPA object as a V1 with a read, modify, write loop, as long as you only modify the spec fields for that particular version. So just in case you're wondering where these things go, and when you just say kube control get HPA, most of the interesting stuff is in annotations, so it's worth pulling down the V2 object. So that's sort of a summary of scale controls and HPA V2 and some custom metrics. So at this point, I think I'll hand it off to Maciek, who's going to talk about the cluster autoscaler.
Thanks, Joe. So yeah, let's talk about cluster autoscaler. What I'd like to do is take you through an example scale-up scenario, and we'll go through it step by step, exploring cluster autoscaler logic to see how it makes its ultimate autoscaling decision. But before we get there, I'd like to do a quick intro/reminder, just quickly covering what cluster autoscaler is and what it does. So, as Joe already said, the job of cluster autoscaler is to provide nodes, or add and delete nodes based on the needs of the pods in your cluster. And more specifically, its job really is to make sure that every pod in the cluster can be scheduled. And to that end, cluster autoscaler takes into account all the same things that Kubernetes scheduler looks at. So this is going to be things like nodes size, nodes allocatable, and pod resource requests, but also things like pods, node selectors, node affinities, pod affinities, host pods, any sort of storage related requirements, and so on. Basically anything that can go into Kubernetes scheduling. What it doesn't look at is metrics, because Kubernetes scheduling doesn't take into account actual CPU usage or memory utilization of the VMs. So neither does cluster autoscaler. For that part, you need workload autoscaling. And before we proceed, there is one more concept that we're going to need, and that is a node group. A node group is basically a set of identical nodes, a resizable set of identical nodes. So whenever cluster autoscaler wants to scale up, what it really does is it resizes a particular node group, adding some number of nodes to it. And the actual implementation of node group is going to be different on each provider. So let's quickly look at architecture of cluster autoscaler. So cluster autoscaler is a pod that runs in your cluster, either on nodes or on a master VM. And it's really made of three main parts. There is the cluster autoscaler logic, the core logic of autoscaler that sort of does the whole autoscaling logic, but there are two important parts that are also there. So first of all, there is the embedded scheduler code. In order to make sure that cluster autoscaler respects all the constraints of scheduling and it actually has the same logic as the scheduler, what we do is we just import the scheduler code and use it to run sort of hypothetical scenarios to explore what would happen if a node was added to the cluster, right? Would that help any of the pods that are currently pending get scheduled? Or what would happen if some node was removed from the cluster? Would all pods running there be able to schedule on some other nodes? And instead of replicating all the scheduler logic in autoscaler, we just import scheduler code and ask it those questions. And the other external part is the cloud provider module. It's basically a rich client to a given cloud provider, so something like AWS or GCE, Azure, or something more abstract like a cluster API. And this is what cluster autoscaler uses to actuate its decisions. Whenever cluster autoscaler wants to scale up, it really, all it does is request a VM from the cloud provider. And then it isn't actually involved in the process of that VM starting up or registering in Kubernetes. All it really does is it make a request to cloud provider. So I think with that background, we're ready to dive into an example scale-up. So what I have here is basically a sort of hypothetical scenario. And there is a cluster with 3 node groups. So as you can see, there is a node group with large nodes that have a label A, and also node group of equally large nodes with label B, and finally a third node group of smaller nodes. And these dimensions of nodes are meant to be some sort of abstract representation of resources available on those nodes. So for example, you can think of it as maybe vertical size of the node would be how many cores it has, and then the horizontal size would be how much memory there is. And similarly, there are a bunch of pods, which also have size, which would be the same. That would be the pod resource requests. And as you can see, some of the pods also have a node selector. So this is to illustrate like other type of constraint that's not resource related, but is also respected by Cluster Autoscaler. So in this case, some of those pods can only run on nodes with label A, which means basically nodes from the first node group. So let's start the hypothetical scenario. We're starting with a bunch of empty nodes and a bunch of pending pods. So obviously the first thing that's going to happen is scheduler will jump in and schedule as many pods as it can on existing nodes. So this is basically what we can see in these slides. All the pods that can fit on the nodes are already there, and the nodes are pretty much full, but there are still some pods that remain. So what will happen with those is the scheduler will say that it cannot schedule them because there is not enough resources available in the cluster, and it will mark them as unschedulable. More specifically, it will set a status condition on those pods. And that is the signal for Cluster Autoscaler to jump in. It basically looks for those unschedulable pods and tries to help them. And the way it does it is it explores those hypothetical scenarios. So the first thing Autoscaler could do is think, okay, what would happen if there was one more of those label A node? Basically, what would happen if a first node group had 2 nodes instead of 1? And to this end, it will create an in-memory fake representation of a node. It doesn't correspond to any real VM or anything like that yet. It's just an in-memory object. And it would ask scheduler, okay, what would happen now, like if you had this extra node? So in this case, the scheduler would be able to schedule some of those pending pods on this new node, but not all of them, right? The one node is not enough to fit all of those pending pods. So Cluster Autoscaler will just continue to do the same. It will add one more identical node. So basically explore, okay, so what would happen if I resize this node group from 1 to 3? And once again, it would ask scheduler, and the scheduler would put more pods on this new node. And basically, we would reach a state where all the pods that are pending could now be scheduled if 2 more nodes were added to the first node group. So that is what we call expansion option. That's basically one action available to Cluster Autoscaler, which would help the pending pods. But of course, there are other possibilities there. There are other node groups. There are other combinations of nodes that could be added. So what Cluster Autoscaler will do at this point is it will just remember this particular expansion option, and it will proceed to evaluate other scenarios. So let's try that. And I'm just going to go more quickly to it right now. So if we do very similar logic where we add nodes for as long as we can put more of the pending pods on them, and we do this process for the second node group, we can see that we could add 3 more of those small nodes, and that would help 3 of those pending pods. However, there is no way we can help the large pending pods by adding small nodes, just because each individual pod is too large. If we think about this, once again, that the horizontal dimension is memory, the small nodes just don't have enough memory to run the large pod. So there is no way we can help them by adding the small nodes. But that's fine. That is an expansion option. So we can remember that we can add 3 small nodes, and that will help those small pods. And we can proceed to the next simulation and explore what would happen if we were to resize the third node group. And the end result here is we can add 2 nodes, and that will help all the pods except the one with the node selector A. There is actually enough resources on those 2 new nodes to run all the pods, but we cannot schedule one of them because of the node selector constraint. So that illustrates that Cluster Autoscaler is also taking this sort of constraints into account. So this is basically how the exploration of various scenarios would look like in Cluster Autoscaler. Note that all the options we're considering is always resizing one node group by a certain amount of nodes, and it's always the largest amount of nodes that actually helps pods, right? So we're not going to consider an option where we would resize, let's say, the third node group by just one node, because adding one more node still helps pods. So we'll just greedily basically bin pack until adding more nodes doesn't help any more pods. And Cluster Autoscaler is also not considering mixed scale-ups. It's always considering resizing just one node group. So after all the simulations are done, we're really left with 3 of those expansion options that we discussed earlier. And Cluster Autoscaler is going to use something we call expander to choose one of those options. Expander is basically just a heuristic that takes all the available expansion options, basically how many nodes are needed to help what set of pods, and it just evaluates them to choose the best one. There are multiple different expanders. There is a random expander, which just chooses a random option. I don't really recommend that one. But there are other, like least ways, like the one that tries to have the least unused resources. There is a pricing expander available for some platforms, which tries to choose the cheapest in terms of dollar cost, like the cheapest option in terms of dollars. And there is also a priority expander, where you can basically, the user specifies a list of preference between node groups, and Cluster Autoscaler will try to choose whichever one is the most preferred. That's particularly useful when you have some sort of much cheaper instances, like maybe spot or preemptible instances. Or you can implement your own expander. It's actually a simple Golang interface, and it's not very hard to implement one. And the one remaining question is, okay, some of those expansion options only help some of the pending pods. What about the other pods? And the answer is, after doing the first scale-up, if any pods remain pending, Cluster Autoscaler will run another iteration and do the whole simulation again and pick some other scale-up, and it will continue doing so until it helps all the pending pods. So that's a very quick overview of how scale-up works in Cluster Autoscaler. And before I end this talk, I'd like to quickly talk about our SIG-Autoscaling group. We have meetings every Monday at 4 p.m. Central European time, and they happen on Zoom. And everyone is, of course, welcome to attend this and ask any questions, discuss any suggestions, and so on. We also have our own channel on Kubernetes Slack, where I think it's quite active. So if you have any problems, I think that's a good place to either ask for help or just engage us for discussing features and so on. And finally, most of our code is in our own GitHub repository. And that's it from me. Thank you very much.
Great. So this is Joseph Burnett here. I'll take some questions about workload autoscaling, about HPA, and then I'll hand it over to Maciek for a few cluster autoscaling questions. So one question I got was, will scale up and down values override the values set globally like the horizontal pod autoscaler down stabilization flag? Will global values affect scale up and down if all you define are the scale values in your HPA YAML file? So when you create an HPA, it is given default scale down stabilization and scale up policies which match the hard-coded defaults which were previous to 118. And those defaults come from that flag and where the hard-coded were. So if you start a controller manager for 118 and you set the flag horizontal pod autoscaling down stabilization equals 10 minutes, and you create an HPA and you load it and you get it back and you look at the value for behavior scale down stabilization window seconds, it will be 600 seconds. So that just affects the default. So all the same behavior is preserved for when you don't set the behaviors. If you do set it, if you add a behavior and say, please, use 5 minutes, it will override the default, which comes from that flag. Likewise for the scale up limits, which are 2x or a minimum of 4. So, hope that answers that question. Let's see if there's any other HPA questions here. It looks like the rest of them are cluster autoscaler questions. So at this point, I'll hand it over to you, Maciek.
Thanks, Joe. So to answer a few cluster autoscaler questions, one that has shown a few times is if cluster autoscaler can be used on-prem. So in general, all cluster autoscaler really does is make a decision to add a new node, but it needs something that can actually create a VM. So you need some sort of private cloud setup, and currently the supported ones is using OpenStack Magnum and Cluster API. I think both of those could be potentially used on-prem. So there is a way to do it if you have some underlying system that can add and remove nodes. But Cluster Autoscaler cannot do it by itself. Okay, so another question is, why does the scheduler need the fake representation if we add a new node? And why cannot it explicitly be calculated how many nodes we need for a workload? So this is because there are multiple different requirements. I tried to illustrate that by using a node selector in example. But there is all sorts of different things with node selectors, node affinities, and so on that I mentioned. So Cluster Autoscaler would need to know about all of this and basically re-implement all of the scheduling logic. And then we would be forever chasing scheduler, and there would be quite a large risk that the two will sort of disagree, leading to potential errors, which is why we try to just use scheduler code instead to just make sure it's actually the same logic and that it's consistent. Okay, so another question is how node selector get the value of new added node. So as I mentioned, node group is expected to be a set of identical nodes. So basically when you have a node already in a given node group, Cluster Autoscaler will just copy it and assume the new node will be identical. And that includes things like labels, basically everything. There is also scale from zero logic available for some providers, and this is provider specific. It tries to somehow guess how a node would look like as accurately as possible, including labels ideally. So for example, on GCP, this is done by parsing instance template, but other providers will have different implementations. Okay. Another question is, are there any plans to open up Cluster Autoscaler so other frameworks can trigger scaling actions? So this is quite complex. The problem here is that Cluster Autoscaler doesn't necessarily have much of a notion of an action. It's really just sort of reconciling cluster. So there is always enough space to schedule all pods. And it's actually it's basically simulating scheduling from scratch every loop. So even if you were to somehow make it add more nodes, in the very next loop, it could figure out that those nodes are no longer needed. It wouldn't remember that it added them, and it would go and delete those nodes. However, there are quite a few like systems or in-home solutions that various people use. And the general idea is a scale-up can be triggered by creating low priority pods. So those pods are basically enough. They just unpause image or otherwise do nothing, and they have a low scheduling priority. So this is enough to trigger a cluster autoscaler scale up, but it's if a pod with a higher priority will be created, a real pod, those pods will be evicted by scheduler to make space for that other pod, and that should be faster than adding a new node. I think we've run out of time, but there is a Slack channel where we'll continue answering the questions. So thank you.